Hello and welcome. Have you ever wondered how a huge application like your social media feed or a big online game can juggle thousands of things all at once without just falling apart? Well, that's the magic of concurrency. Today, we're going to dive into how Java manages all this complexity, turning what could be total chaos into perfectly coordinated action. So here's our game plan. We'll start by looking at the core problem. What happens when tasks literally collide? Then we'll explore the tools Java gives us to take control, let those tasks communicate, and build them in a smart way. We'll also face the ultimate danger, gridlock, before we pull it all together in the end. All right, so to really appreciate the solution, you've got to see the problem in action. And in the world of multiple threads, that problem is basically a frantic, unpredictable race that leads straight to chaos. Let's start with a really simple question. Imagine you've got a number, a counter. Thread A wants to add 1, and thread B wants to add 1. If that counter starts at 0, the answer should be 2, right? Simple math. Well, not always. This right here is called a race condition. It's a nasty kind of bug where the final result of your code totally depends on the unpredictable timing of who does what and when. It all comes down to which thread wins the race to the finish line. It's the kind of bug that can drive you crazy because it might just disappear when you try to look for it. Okay, so check this out. This is how that error actually happens. Let's walk through it. Thread 1 comes along and reads the value, which is 0. But right before it can save its new value, the system pauses it. Now thread 2 swoops in. It also reads the value, which is still 0, and it adds 1. Thread 2 finishes its job and saves the result. The value is now 1. Finally, thread 1 wakes back up and saves its result. But remember, its calculation was based on that old value of 0, so it also writes 1. The end result, we added 1 twice, but our final value is 1, not 2. Our data is totally wrong. So how in the world do we prevent this kind of chaos? Well, we need rules. We need a system to make sure that only one thread can mess with our shared data at a time. And to make this super easy to understand, we're going to use a simple real-world example, a restaurant. So just imagine that shared counter from before is a really popular restaurant, and all of our threads are the customers trying to get service all at once. If every single customer just rushes the kitchen, you get chaos, right? We need a system. In Java, every single object has a built-in lock called a monitor. The absolute best way to think about this is like it's the key to a private dining room in our restaurant. Only one customer, which is our thread, can have that key and be inside that room at any given moment. Everybody else, they have to wait outside until that key is free again. Now, we use the word synchronized to tell a thread it needs to grab this key before it can proceed. You can synchronize an entire method, which is kind of like locking the entire restaurant just for one customer. Or for way better performance, you can use a synchronized block to lock just a specific tiny part, like locking only the kitchen. This is great because it leaves the rest of the restaurant open, allowing other threads to do other things that don't conflict. It keeps the whole application running smoothly. Okay, so locks give us control. They stop threads from running into each other. But what happens when threads actually need to coordinate? What if a thread gets the lock, but then realizes it can't do its job until another thread does something first? Let's head back to our restaurant. A customer gets the key, they go into the private room, they're all ready to eat, but their food isn't ready. The kitchen hasn't made it yet, so what are they supposed to do? They can't just sit in there holding on to the key, making everyone else wait forever. If they did that, the chef, our other thread, could never get into the room to deliver the food. The whole system would just grind to a halt. That customer needs a way to give up the key for a little while and just wait. And this is where Java's wait and notify system comes in. It's pretty brilliant, actually. When our customer thread realizes it can't move forward, it calls wait. This does two things. It gives back the key, releasing the lock, and it goes into a waiting state. Sometime later, our chef thread comes along, grabs the key, does its work, and calls notify. That's like the chef tapping one customer on the shoulder and saying, hey, your order might be ready. Or it could call notify all, which is like the chef yelling order up to every single waiting customer, waking them all up to check if their food is ready. Now here is a classic trap. You might think that once you get notified, you're good to go, right? So you write your code with a simple if statement. But this is a really subtle and dangerous bug. Why? Well, because another hungry customer could sneak in right after you get notified, but before you get the key back, and steal your food. So the correct way,
The only truly safe way is to always put your wait call inside a while loop. This is so, so important. When your thread wakes up, it gets the key back, and then it immediately rechecks the condition. It asks again, is my food really here? If the answer is no, it just goes right back to waiting. This protects you from any shenanigans that might happen after you get that notification.
So we know how to control our threads and how to make them talk to each other. But getting the logic right is really only half the battle. How should we structure our code to begin with to make sure it's clean and flexible? Let's talk about the best way to actually build our threads. You've basically got two main ways to create a task for a thread in Java. You can either extend the thread class itself, or you can implement something called the runnable interface. And the consensus is pretty clear. Implementing runnable is almost always the better choice. It separates the task, the what you want to do, from the worker, the thread itself, the how it gets done. This is way more flexible, it's better object-oriented design, and it leaves your class free to extend some other class if you need to. We've learned how to manage our threads, but there's one final catastrophic problem that we absolutely have to learn to avoid: the dreaded deadlock. Deadlock is the ultimate programming traffic jam. It's when two or more threads get stuck in this circular waiting game. Thread A has a key that thread B needs, but thread B has a key that thread A needs. Neither one can move forward, and so they're just frozen forever. Let's make this crystal clear with a little story about Wilma and Betty. First, Wilma grabs the lock for resource A. Easy enough. Then Betty comes along and grabs the lock for resource B. Now, Wilma decides she needs resource B, but she can't get it. Betty's holding it. So Wilma waits. Then Betty tries to get resource A, but guess what? Wilma's holding it. They're now stuck. They're deadlocked, each waiting for the other, and the program just hangs forever. Whew. Okay, we have covered a lot of ground, from the very basic problem to the most dangerous pitfalls. So let's do a quick recap of the essential tools for our concurrency toolkit. All right, let's lock in these 5 key ideas. A race condition, that's the problem we're trying to solve. Synchronized is our solution, it's the lock and key. Wait and notify are how our threads coordinate with each other. Implementing runnable is the best way to design our tasks. And finally, deadlock is the ultimate danger that we always have to watch out for.
And that brings us to the end. But, these ideas, they're not just for code. Think about a busy traffic intersection or a global supply chain, or even just two people trying to have a conversation. Where do you see systems that need locks and coordination to prevent these kinds of race conditions and deadlocks? Once you start looking, you'll see these patterns absolutely everywhere. Thanks so much for joining.